Welcome, everyone. My name is Chris Neidl. I am one of the co-founders of the OpenAir Collective, and I'm really excited to have you all here with us today for this latest installment of a special COP27 Carbon Crowd presentation. And in the Carbon Crowd series, which we're introducing here at COP, we're talking to innovators around the world working on different forms of CDR who think that one of the keys to accelerating innovation and breakthroughs and ultimate success is by opening up that technology with a broader community of people who are invested in it and that can help improve it and evolve it into a successful form of carbon dioxide removal. And today I'm incredibly excited to be joined by Mike Bwondera, who I've now known, I think for probably about a year and a half ago, we first met, and a lot has changed since we first did meet. Mike is based in Kenya, and he's part of the senior engineering team of Octavia Carbon, which he'll explain a little bit about. But this is a DAC development company based in Kenya. And Mike will get into this in his introduction, but often when we think about direct air capture, a lot of the news is focused on places like Iceland or in, innovation centers in the Northern Hemisphere, places like Silicon Valley and other places. And sometimes we overlook other areas where there's enormous potential to deploy direct air capture. And East Africa and Kenya are absolutely on that list. And that's because one, very abundant geothermal energy there that's barely been tapped, which integrates really, really well with DAC as a power and heat source. So there's an enormous amount of that. Also an enormously favorable geology. There's just huge amounts of basalt, which is an ideal storage medium for carbon storage. But the third and maybe ultimately most important element, and this is as someone who worked in Kenya for some time on solar projects, is the human capital in Kenya. The level of ingenuity and entrepreneurship that I think is part of the culture in Kenya is a very impressive thing to behold. And we think that bodes very well for DAC, that there's people like Mike and his team at Octavia that are really starting to turn serious attention to this. So, Mike, it's a real pleasure to have you here. I'm also joined by two OpenAir veterans. Some of you will know Charles Yang, who is the host of CDR Horizons, an excellent YouTube series that OpenAir produces that Charles moderates and hosts. And we also have Alex Ossie, who's a very active contributor to OpenAir's R&D community. He's based in Oregon. Charles is based in Virginia. And I wanted to bring them along because I thought they would find the project quite interesting and would probably have more intelligent questions than a policy guy like me to ask. So we'll go ahead and get started. Mike, great to see you.
Great to see you too, Chris. Thanks for having me. And thanks for joining Alexander and Charles. So just as Chris has said, my name is Mike Bwondera, and I am an R&D engineer at Octavia Carbon based here in Nairobi. So just a little about myself. I recently graduated from the University of Nairobi. I was doing a bachelor's degree in mechanical engineering. And once I was while still in school is when I was actually introduced to the idea of direct air carbon capture. And a thing about me and most of my peers, what we kind of say about ourselves is being engineers, we kind of usually like solving problems, and climate change is one of a really key issue that we're having in the world right now. Like currently speaking, Kenya is actually facing a really major drought issue. And climate change, even for our new government that's just come in recently, climate change is one of the key issues that the government intends to focus on. So yes, I got to know about direct air carbon capture last year, and I was really interested in actually doing a project, actually coming up with a machine that can do such. And that's when I actually got in touch with the OpenAir collective, met with Chris, and Chris also introduced me to Martin, who happens to be a colleague of mine here in Octavia Carbon. So Octavia Carbon is actually Africa's first direct air carbon capture company, as far as I know. And we are actually a really young company just focused on cost effectively building and deploying DAC in Kenya. So here, right now, in our first 5 months, we've actually, which I will be presenting today. And if you'd ask why is Octavia, why Octavia, why should we kind of give Octavia Carbon some importance or some attention rather, is that we actually kind of plan at getting the dark cost down. And this kind of we can draw analogies to solar PV technology, whereby decades ago it was quite still novel and expensive to deploy and all, but companies in China were the one who actually were able to take such a technology and make it more scalable, and we actually enjoy what solar is today. So same thing here as Octavia Carbon, we actually find a lot of importance on our side to actually be able to prove that direct air carbon capture is not only this kind of new expensive technology that's only limited to people who specialized PhDs in chemistry and all that, but it's actually something that can be widespread to a number of people, even in developing countries like ours. And this, I think, is actually really key in scaling up carbon capture and making it quite cheap. So yeah, for now, we actually are open sourcing our technology platform for others to join us in building this supply chain that benefits all of us. And Chris had touched a bit onto it. Like Kenya is also quite an ideal place to scale global dark deployment and manufacturing because of our suitable geology. We actually have abundant renewables, especially in geothermal energy. We have cost-effective talent for manufacturing, especially large-scale manufacturing. And also as CO2 as an industrial gas, I mean, we have quite a deep market for direct air carbon capture carbon dioxide, because as of now, suppliers of carbon dioxide are quite limited here in East Africa, and so we could tap into a market of providing cheap carbon dioxide for industrial purposes. Yes, I think that's on the introduction side, and I'd want to present some slides on ideally the technical side of our project. And I'd also say our project is called Thursday, and I mean, I can elaborate later on why we chose the name. But for now, does anyone actually have any questions before I continue?
Well, let me just quickly, because I didn't say it at the beginning, the focus obviously we want to talk about, you were just laying out the rationale for DAC in East Africa, touched a little bit upon the focus of Octavia as a DAC development company, but that strategically over time is interested on taking on more and more of the value chain of DAC, even potentially technology development and manufacturing locally, which is really, really exciting. But what we're really going to drill down to today is how quickly you guys really got going on that and have already developed your own direct air capture machine, which you just referred to as Thursday, which we will ask you to explain where that cool name comes from, that you're using initially for outreach and education, but it's a functional unit. And you're going to tell us more about it. We want to see how far we can take it, I guess, in terms of evolving it into something that has really enduring use value. Charles, looked like you maybe had a question, though.
Yeah, no, this is super interesting, Mike. Really appreciate you sharing about your work. I'm curious, so it's really cool that you all are focused on manufacturing and open sourcing. I'm curious, like, what does open sourcing look like for you all?
Well, for now, open sourcing would be mainly showcasing our technology, both on the mechanical design side, on the chemical chemical solvent preparation side, and on the control system side, like the code for sequencing of components and all that stuff. I don't know whether that answers your question.
No, that does. That's really cool to hear that you're open sourcing like every part of the system, really. So yeah, really looking forward to the technical presentation as well.
Great. Yeah. So Mike, please do. If you have some slides, you can share those. And then I know you're going to give us an actual tour of Thursday, but maybe you could start off, if it's not part of your presentation, of telling us about where the name Thursday came from for the name of your unit.
Yeah, so it's quite simple. It's because the first time we actually unveiled our machine to someone who's not a part of Octavia Carbon was actually on a Thursday. It was at one of the recent Nairobi, they're usually called Nairobi Climate Net Nights, and it's actually some sort of networking event held monthly, where people around in Nairobi who work, in climate change and stuff meet. So we actually unveiled it on a Thursday, and that's
great. And while we're here, what was the response? I know that DAC is new everywhere, but that was probably the first time somebody rolled a DAC unit into one of those meetings. I was wondering just what were the kind of questions you got, or what was the general response?
Yeah, people were quite surprised. I mean, the general response was quite positive, and people were, pleasantly taken aback by how a small company in the global south is actually in the forefront of a quite new technology globally. And yeah, there was a lot of curiosity, a lot of questions on how we were able to do this in such a short time and all. But yeah, generally speaking, just a lot of positive feedback we got.
Excellent. Great. Well, if you'd like to share your slides, we can go through those first.
Yeah, sure thing. Yeah, cool. So most of this initial part is actually just what I had explained, and I'd want to start on the technical side of things. So as you can see, this is a picture of Thursday on how it looks like, and I'll just take you through some of the components as you can see on the screen here. So we have, it's actually an assembly of a number of components. As you can see, we have an inlet fan on the left side of the screen, and then an inlet damper, a sorbent chamber, an outlet damper, and an outlet fan, and a low pressure buffer tank, a vacuum pump, and a compressor are actually the main parts of the machine. So others are actually just auxiliary parts that help everything come in place. So just a brief description on what everything does. It actually seems a bit quite self-explanatory. So the fans are actually, they facilitate flow of air through the sorbent chamber, which actually facilitates absorption of CO2. So we opted for two fans initially because we were thinking about pressure drop, which is one main factor that we had to consider when designing our sorbent chamber. So we felt like having two fans would be enough to actually resist the static pressure of this should I say, long system. And dampers are just used for controlling the flow of air, either once we actually do our absorption or desorption. We would need to control the airflow, and that's essentially what the dampers do. Yeah, the sorbent chamber holds our sorbent material, and as you can see, it occupies quite a large surface area, and I'll go into detail on why we actually did that. The vacuum pump and the compressor, they are mainly gas transfer. In this case, it's carbon dioxide, mainly for gas transfer. And the low pressure buffer tank is actually just a tank that we put in place because we wanted to, when we were designing our system, we couldn't quite ascertain whether desorption flow rates of desorption rates of carbon dioxide would be smooth and consistent. And we wanted to have a low pressure buffer tank where actually, which kind of simulates a mass of CO2 or around a mass that would kind of equate to what the mass that we absorb per cycle, we dissolve, I mean, per cycle, and kind of simulate that in atmospheric conditions, so that once we can actually compress this into like a high pressure tanks, and this would ensure that the compressor actually has like a consistent inlet instead of just doing it directly from our sorbent chamber, which at that time we couldn't really ascertain whether we'd have consistent desorption. So most of these factors, I'll explain it here. Like, yeah, our CO2 capture area, we needed it to be quite large enough so that we can maximize the absorption of carbon dioxide. So yeah, we made the sorbent chamber to be as wide as possible, which is roughly 1 meter squared, to increase the contact area for carbon dioxide. Horizontal airflow, what actually made us go with such a design is we actually thought we didn't want inlet and outlet air to mix, because essentially if your outlet air would kind of be mixing with your inlet stream, that would reduce your efficiency, your carbon dioxide capture efficiency. So that was why we went for horizontal airflow. And as I had explained earlier on, the sorbent chamber was made to be as thin as possible. It's actually around 4 centimeters thick, as we wanted we wanted to limit the total static pressure drop across the machine. So we actually noticed in our design, if we had like a sorbent chamber which occupied a much smaller surface area, but kind of was deep in its thickness, we'd have a lot of static pressure that maybe finding fans that would actually overcome that would be quite difficult. And that's why we made it as thin as possible, and also that detects on why it's also quite large in surface area. So also considering the corrosiveness of carbon dioxide, most of the body of this machine is made with stainless steel. The chutes, the transitions, the solvent chamber in itself, and all also the linings of the low pressure tank, they're all made from stainless steel to actually just check on the corrosiveness of carbon dioxide. And lastly, as I had explained earlier on, the uncertainty on the desorption flow rates is why we actually went for a low pressure buffer tank that could hold about 0.5 kilograms of CO2 at atmospheric pressure, which is about the same amount of CO2 that we'd obtain after every absorption-desorption cycle. These are the major design factors that I put together to actually show why Thursday looks the way it is. And yeah, so on the control side, I'll talk a bit about hardware, and definitely in every sort of control system, you'll always have you'll have your input devices, your controller, and your output devices. So we went for an Arduino-based system, and Arduino is probably, if there's anyone who doesn't know about Arduino, it's actually just an open source automation a control system whereby you could use an array of input and output devices, and also like microcontrollers to kind of control any sort of equipment that you have. And we actually found it really conducive for our application because, first of all, it's open source, so we don't have to pay quite a lot to just get access to like a control system software. And also the fact that there are quite a lot of components, electronic components, that are compatible with Arduino. So those are the two main reasons why we went with an Arduino-based control system. So our microcontroller was an Arduino Mega, which is just a microcontroller board based on the based on an Arch chip, which has quite an array of input pins for sensor data and both digital and analog output pins. So digital output pins are for when we kind of just want to trigger certain components to either come on or off, and analog pins are when we actually needed some sort of modulation for our devices, maybe if it's something to do with varying speed and all that. Yeah, so another relays, we used relays, which are just the electromagnetically controlled switches that open and close circuits to the various electrical components, and which we receive the control signals from our microcontroller, which is the Arduino Mega that I just talked about. Yeah, so when it comes to the sensors, the main thing are the CO2 sensors, and what we could find cheaply are SCD30 CO2 sensors. I think we got them from a company based in China called Seed Studio. And yeah, they're CO2 sensors which have a measuring range of 0 to 40,000 ppm. Definitely, we'd want something that would get to a million ppm with quite high precision, but we found that this was at least sufficient for controlling our adsorption and desorption sequencing. We would use these sensors, place one upstream and another one downstream of our solvent chamber, and this would kind of dictate to us when our adsorption period would stop and when we could start desorption. Yeah, we also use a small pressure sensor. It's a BMP 280, which is also in quite kind of it's just a small chip which you place inside the solvent chamber, and it sends pressure values to our microcontroller. And this pressure sensor we found it essential to actually give us an idea of when we could start our desorption process, in that once we finish adsorbing, let's say we were adsorbing for maybe 2 hours or so, and we've got the valid information from our CO2 sensors that point us to start our desorption process. We found it important to first of all kind of evacuate this solvent chamber that we have, and that's also why we have a vacuum pump, so that we can limit the amount of ambient air already inside our solvent chamber. And also we know that vacuum, having some sort of partial vacuum doesn't hurt when it comes to desorption. So we have a pressure sensor that can also measure vacuum pressures that help us kind of sequence our desorption. We also have temperature probes which are inserted into our solvent material, because we know the solvent that we opted to go for actually dissolves. It's a temperature swing solvent which dissolves at relatively low temperatures, and you have to also take care that if you get past 80 to 90 degrees, our solvent would start kind of degenerating and even at some point charring. So we had to kind of limit the desorption temperature. And so that's why we actually had to insert probes into our solvent chamber. And yeah, accelerometers were just kind of a safety measure which were attached to our dampers, which just ensure that the fan doesn't start when our dampers is closed, to limit that resistance to airflow, which could end up affecting both the dampers and the fans. Yeah, and that's much on the control system side. We also have an array of solenoid valves that I haven't talked about yet. So solenoid valves are just basically help us kind of control the direction of gas flow, and they are also part of the control system and are also actuated by our relays. Moving on, we have our sequencing. I hope this flow that is visible enough. But so to start, we first kind of want to measure the pressure and see if CO2 is negligible. So what I'm trying to say is we start our process by kind of first checking the CO2 ppm values that we are getting from our inlet CO2 or our upstream CO2 sensor and our downstream CO2 sensor. So once you absorb, and once your absorption pressure, your absorption process continues, the assumption is the values of CO2 downstream of your solvent chamber will actually be lower than the values of CO2 upstream of your solvent chamber. So this condition is actually checked by our control system, whereby if the difference of the upstream and downstream CO2 sensor values are more than a certain threshold, that means that your solvent is not yet saturated and absorption should continue. So by absorption continuing is where now we open our dampers, which are christened D1 and D2, a small delay, and then actuate our fans, and that now would start the airflow through the solvent chamber. And once that is off, once that is also continuing, we also ensure that all the solenoids and all other gas transfer components are shut off, to ensure that it's only the absorption process where air is flowing through the solvent chamber that's happening. Once we get to the stage whereby and so as absorption continues, we found it makes sense, yes, and we actually proved it, that the ppm values of your downstream sensor actually just slowly start coming back up until it reaches to a point whereby the values of your CO2, the ppm values of your sensor upstream and downstream are more or less equal, and that indicates that the solvent inside the solvent chamber is saturated with carbon dioxide and can't take any more carbon dioxide. And that's when we'd start our desorption process. So the sequence, first of all, is that we'd evacuate some excess air outside our solvent chamber. And that's why we'd first turn off the fans, close the dampers to ensure we just have a controlled volume, which is the volume around the solvent chamber. And then we open an array of solenoids that direct airflow outside of the system, and just actuate our vacuum pump to blow excess air out of this solvent chamber. And then afterwards is when we close all the solenoids again, and start once actually a pressure threshold is met. Once we get to a vacuum pressure, which for our design we were looking at around an absolute pressure of around 200 millibars or so. I don't know how much that is in PSI. I'm sorry if we use metric here. Once that pressure threshold was met is when we could now actually start dissolving our solvent material. And that for our case, we used a temperature swing solvent. We have a heating system which is based on resistive heating, and so we'd actuate that, start heating the solvent, and desorption of carbon dioxide would start happening. And this would continue happening up to a certain point where also another pressure threshold would be met. And from that, we could now start moving CO2 into our low pressure buffer tank. And from that, once we actually get a pressure threshold into our low pressure tank, is when now we'd actuate our compressor and now compress this CO2 into higher pressure tanks for storage and also further analysis. Yeah, so that was just a quick walk along on how the sequencing of our components happens. And another important work stream is the solvent preparation, which we also had to ourselves. So we used solid supported amines. So essentially, the amine we went for was polyethyleneamine, and we used silica gel, or rather silica powder, as a solid support. And the process was a wet impregnation process with a 45% PI loading onto the silica gel. And methanol in this case, we also use methanol as a solvent because we found that PEI as a liquid is quite difficult to handle. It's quite viscous. It's like glue, and for that we actually since it properly fully dissolves in methanol, we used it as a solvent, so you can facilitate the mixing of PEI and silica gel. So I'd like to point out that on the chemical work stream, we actually got a lot of help from various chemical researchers, because someone like me, I can tell you, I'm not a chemical engineer, and yeah, we had to read through a lot of papers, and just kind of from the information we got, we also got help from guys from like the University of Limerick and such, and from that is when we could now come up with our own process and try to see what we could come up with would be effective to actually absorb a good amount of carbon dioxide. So as you can see here, this is a setup that we had done. It's kind of bootstrappy, as you can see, but what I know you can see naked wires and all in this picture, but I can assure you we actually made things more neat. So this was actually a picture taken once we were testing out if what we were trying to do would actually be working. So one issue we had on the chemical work stream was that a lot of papers that talk about the different solvent alternatives that you can use for dark, that show like promising results of maybe for example this mixture of polyethyleneamine with silica gel as a support. Papers will talk about capture efficiencies exceeding 1.5 moles of carbon dioxide per kilogram of solvent. But now the issue we were having is now that this kind of processes done in controlled environments like specialized labs, and it would be like gram scale amounts of solvent material. And now we're in this situation where we want to kind of try to get to 6 to 10 kilograms of solvent materials or thereabouts, while just kind of repeating the process of the procedures that we've learned on from the various professionals, I should say, on the chemical side of things. So the process we needed to figure out ways of actually doing this wet impregnation properly, and that involves a lot of mixing, like stirring continuously for 12 hours or so, or heating, providing heat at 60 degrees or something for 12 hours or so, drying for 24 hours, and all those processes. And we were quite limited on specialized equipment, so we had to find way more creative ways of actually trying to do this, and I'll go deeper into that once I finish this presentation. Yeah, so our concept, our talking about Thursday, the advantages we could draw from it so far are our overall power consumption is quite low, and as you can see, our fans actually this is actually once both the two fans are in operation, we draw about 315 kilowatt hours per ton of CO2. Our heating system, and this is also quite a conservative value, because we for the heating, this actually we dissolve for probably like an hour or so, and this value actually depicts a continuous dissolption for 1 hour. But we actually noticed, in order to control our temperature, and we kind of have a situation whereby we monitor our temperature levels, and that would involve a lot of heating, and then you kind of stop heating, and that happens a lot within that hour. So the conserve this 1,154 kilowatt hours per ton of CO2 actually kind of depicts if we just left our heating system on for an hour. So yeah, and the other components like the vacuum pump, the compressor, the solenoids and all would take around 320 kilowatt hours per ton of CO2. We also believe we used a cheaper formulation, used something like PI and silica gel. We thought that there are cheap alternative to most other kind of specialized solvent alternatives like metal organic formworks, and also still looking into amines with solid supports. They were also like solid supports like SBA 15 and MCM 41. I can't go quite much into these details because, like I said, I'm not a chemistry professional myself, but we knew that these are some chemicals which are quite expensive to obtain. We also used cheap and locally sourced fabrication materials like the stainless steel to construct the body, the dampers and stuff. And we found that sourcing them locally would really be a bit cheaper, and as compared to having to source them like internationally in bulk. So that's also another advantage you can draw for Thursday. So we have quite a large footprint, and we actually found that we could have even with like high CO2 capacities, we could even still make our design more compact, facilitating assembly, transportation, and deployment. The really high solvent chamber volume also it means that our CO2 dissolves into quite a huge volume, and that increases chances of it mixing with air due to the difficulty of properly evacuating this chamber. So another solution we found is we could like entirely discard our low pressure buffer tank and use this whole solvent chamber volume as a buffer tank in itself. And yeah, on the control system side, we found that long wiring would affect the data transmission capacity of our sensors, and that would kind of have implications on the automatic sequencing of our concept. So that's wireless transmission is one thing we were looking into. And also, yeah, when we were doing our design, we didn't really consider a lot on the electrical cabling provisions, and sometimes we'd find our wiring all over the place, and that's something that we definitely just have to improve on. Yeah, that's it on my presentation. I think I'll stop sharing my screen for now.
Great. Amazing. You are a true engineer listening to you go through this. Well, Charles and Alex, do we want to just quickly see Thursday? And then we can ask some questions. Yeah, let's see.
Let's see it.
Okay, so right now this is a test of our machine, and we'll start with the adsorption side, which involves blowing a stream of air right through the machine coming from that side, blowing to the exits. And what's happening right now is that the dampers, which are essentially butterfly valves similar to the throttle valves of a car's engine. So as you can see now, they're actually opening. They're in the process of opening both on the exit side and on the entry side. They usually take about a minute or so to open. So right after they finish opening, these fans on both ends will actually actuate, and they will actually just push air through the system. And right here we have our solvent chamber. So as the fans blow air through, will actually the adsorption process will actually continue. So the solvent material will be absorbing carbon dioxide. So any moment from now, we'll hear the fans actuate. So those are the fans. So for this test, we made them actuate for about 30 seconds or so, just for a test. But this process would essentially take about 3 hours or so once we're in full operation. So after the 30 seconds, now we want to start our desorption. So the desorption will have to close off this solvent chamber, and this will actually involve closing off the dampers. And as you can see, as we wait for the minutes to end so that the dampers can close, I'll explain a bit on the desorption side. So it will involve heating our solvent, which is inside here, and as the solvent material is heated, it will release, or in other words, dissolve carbon dioxide. And this dissolved carbon dioxide will actually be transported be conveyed by this vacuum pump, as you can see here, from this chute or the sorbent chamber in itself into this big low pressure tank, which will act as a buffer tank for further which will act as a buffer tank, and a compressor here will actually take this carbon dioxide to another high pressure tank for later use. So any moment from now, the vacuum pump will actuate. And then any moment from now, the compressor will actuate. Yes, so those two actually just signified the entry into the this buffer tank, and once this buffer tank is actually filled with carbon dioxide, this compressor, as you just heard, will be conveying this captured carbon dioxide into a high pressure tank, which can now store a lot of mass of carbon dioxide for the use case that we want.
Incredibly cool, man. Like, you guys just in such a short period of time did this, which is just really amazing. I can't wait to hear a little bit more about the other research you did to come to this design, but we'll talk about that in a minute.
It's super cool to see, and yeah, anyone on the OpenAir R&D side would be very excited to see all the work you put into this.
No, Mike, definitely this is like the most serious work I've seen, that people thoughtfully trying to make DAC cheap and accessible while in a manufacturing kind of way, and open source. So this is really cool.
Yeah, validating to see that that other researchers have come to some of the same conclusions as us. From Arduino, from kind of cheap sensors, to the kitchen equipment repurposed for sorbent prep. It's good to see.
And that's the particular brand of ingenuity I've seen firsthand in Kenya, is just in solar. Just the creativity that is unleashed when you're operating with bootstraps is pretty breathtaking sometimes. I think we just saw a nice dose of it over the last 20 minutes. So yeah, it's amazing to see this in person. Must be an interesting roommate to have. And we'll spare the audience the incredible epic. You guys were trying to get that unit to COP27 at Sharm. You did everything you could to try to get it shipped out, and ultimately we had some logistical time, so we're gonna have to bring that to COP28. But it's really just a thing of beauty, I would say, that just exudes creativity and ingenuity. I'm gonna let the two smart people on the Zoom, or two of the three smart people, go ahead and ask some questions if you guys have some about the design.
Yeah, Charles, you want to go first?
Yeah, sure. First of all, I just want to say, Mike, this is super cool. Like I said earlier, it's rare to see a group that's working so thoughtfully on how to scale manufacturing in such a comprehensive and also open source manner, which I think is really commendable. I guess the question I think that's always top of mind is how much is it going to cost? Have you done like a cost estimate on like dollar per ton of CO2? And you mentioned some of the ideas, but do you want to give like a short list of some of the de-risking activities you're doing to help lower the cost? I know you mentioned the heating period already, and maybe lowering the buffer. But if you want to just talk just briefly on that side of it, be curious to hear your thoughts.
Oh yeah, sure thing. We the whole machine itself, even without kind of talking about costs per ton of CO2, we spent somewhere around a total of $6,000 to actually come up with this concept. And yeah, we definitely, this is kind of our prototype, and we definitely know that we needed to improve a lot of quite a number of factors that we needed to look into again to actually make this cost quite low. So I don't want to say this cost actually is inclusive of everything, even like the solvent, actually buying the solvent chemicals, which were really expensive on that front end. Yeah, so our main thing that we're looking into right now, number one, is the cost of materials to actually build it. And as I had said earlier on, we think we can actually get this to a lower footprint, and we'd reduce the amount of stainless steel that we'd need to actually make this. Another thing is on the electrical side of things. I think there's some things that we had initially thought of. We initially over designed to just compensate for any sort of uncertainties that we're actually noticing we might have not needed. Like I had explained earlier on, something like the low pressure tank, which was really costly. Other things were like the fans, which you actually noticed we could modulate the fans to quite lower power consumptions. Yeah, and also on the chemical acquisition side, we could find we use Chinese suppliers of the chemical the solvent materials, which I guess aren't the most trustworthy in terms of chemical efficiency and stuff. But yeah, there's we still think it would be a better alternative cost-wise. So right now I can't give you proper like really solid estimates of the cost per ton of CO2 right now. That's something that I can easily just forward it to later on. But yeah, I'd say our main considerations on actually just reducing the overall cost would be on the overall cost of materials and the the power consumption, I mean. So
Yeah, fantastic. And yeah, I will reiterate, I think anyone in the open source DAC world would be super excited about everything you presented. And really cool to, yeah, take a, it's really the only pathway that's been commercialized is temperature swing, and to see someone just go and build one, really cool, really exciting. Yeah, I guess my question has to do with sorbents. You mentioned that you do see some degradation at higher temperatures, so you just kind of shut the machine down. I'm curious kind of what that looks like, and sort of, do you have a sense of how long your sorbents are going to last? And then if they do break down, do you have a process for regenerating them, replacing them in the machine, or what does that kind of look like?
Yeah, so on that, funny enough, we found out our sorbent to be quite stable and reusable below temperatures of 80 degrees or so. So past that, it actually gets a bit tricky to control its regeneration, because one thing we noticed is, for example, our solvent is a white powder, because it's mainly the silica gel as a support. And once you get to temperatures of around 90 to 100 degrees or so, it would start charring a bit and turning quite yellow. And once you get past 110 degrees or so, it would now fully char and turn black. And this would actually really spread quite fast, and that damage the damage is irreversible. So from what we've worked with so far, we actually just noticed that keeping it under 80 degrees or so is a safe place to be in terms of ensuring that our solvent is still reusable. And we've done full absorption and desorption cycles for probably 3 times or so. And yeah, there was actually one time when we noticed there were some issues in the design of our electrical resistive heating, whereby just a small part of the solvent started charring, and this was mainly because we had unknowingly used some sort of plastic wrapping, which helped us. We designed our electric our heating system in such a way that we'd use thin nichrome wires and just kind of mold like clay around it to ensure, first of all, that we ensure that it's actually not a fire risk, because nichrome wire on its own gets quite hot, and that would be hazardous. So we used clay to actually first of all retain the temperatures once we stop supplying current to this nichrome wire, and also limits the temperature rise that happens with the nichrome wire. And so with this plastic wrap that we unknowingly still left in there, it kind of started getting charred a bit, and this started spreading a bit onto a little bit of solvent material that was next to the plastic wrap. And what happened was the solvent started charring, and you could actually notice some sort of smoke forcing its way out of the chamber. And we were lucky enough that it was only such a small part of our solvent we mitigated it quickly enough before it continued. The effects kind of continued spreading through the rest of the solvent. But yeah, we actually noticed that the best bet that we have is actually just being really careful with the temperatures that we get to once we're actually doing this option.
I noticed as well, the energy consumption for the heating component is really sort of your top consumer.
Yes.
So is this sort of is this kind of your top priority for future research? And have you, I guess, looked into doing kind of clever things like using kind of like heat pump style technology and things like that, or is that just like too complex for this project?
Actually, it's good you asked that, because we have decided, especially for power reasons and also for safety reasons, we want to look at another alternative that's different from resistive heating. And we were thinking about using some sort of heating medium, a heat exchanger, maybe hot water, maybe steam. And we'd want to actually look into the power consumption implications of that. But for our next design, we'd actually go for something that like a heating medium kind of system, which might be hot water or steam. We'll actually do a little bit more research on that and come up with a definite answer. So yeah, definitely the heating system is a major point of improvement on our concept, and we're currently just looking for better alternatives to deal with that.
Taking a step away from the technical for a second, I'd be curious if you could share a little bit about the team and maybe the journey, like how big is it? How did you all come together? And also keeping in mind that there might be, funders or nonprofits on the call or watching this. $6,000 for a single concept sounds like a great deal to me. What is like kind of your, I guess, financial situation, and if you have any asks or anything on the horizon that you'd want to share with the broader community?
Okay, so we had a pre-seed round of investment, and we were able to raise $100,000 of pre-seed investment. And we found that this would actually help us to get at least to our prototype, and after that, some sort of MVP that would be much of an improvement from this prototype. And with that, we are looking to have a seed round of investment later on in the future, once we actually have a proper working MVP. But as for now, we'd be open to, like I said, we'd be open to other investment rounds later on. But yeah, right now I think we have the capacity to kind of get to sort of an improved version of Thursday. And you also asked a bit about the team. So right now we're currently eight people. We have there's Martin, who's our CEO, and then we kind of split ourselves into mechanical, electrical and control system, and then chemical. So we have most of the workforce in Octavia is actually just university graduates. So like on the mechanical side of things, we have 3 recently graduated mechanical engineers, myself included. We have 2 electrical engineers, and we also have 1 chemical engineer, and we also have like 1 business administration associate who helps us on the business development side. Yeah, so that's our team. I hope I was able to answer your question.
Yeah. I mean, 8 people and $100,000. That's a lot of cool stuff you can do with that.
Exactly. Yeah.
Definitely. And so we're just about at time. And I just want to, underscore how excited we are and how much what you're doing is the absolute just apotheosis of what OpenAir really is about and hopes to see in the world. And we're so excited that it's coming from your team. But I want to just give the audience in the show notes, there's a form that you can fill out if you're interested in not only following this project, but participating in it. And this is what we really want to do. Charles raised it at the beginning of what's the point of doing open source. And Mike mentioned the different things that will be visible open source. But the purpose is how do we help out under Mike's leadership, bring in as many eyeballs and brains and different people from around the world who are invested in this idea to help troubleshoot and help evolve this within the context of a global community. And we're going to really get going on that in the very beginning of 2023. In the coming weeks, you'll see the documentation for the project will be posted on GitHub. And then we're going to really start community building. And so if you're interested in learning more from Mike and his team and offering your ideas, insights, and sweat to try to make this amazing, because I think you probably got a sense from hearing Mike, this started off as a sort of a demonstration project, but just hearing you talk, Mike, and knowing that some of the DAC companies in other parts of the world aren't that interested in coming to Kenya. So maybe the answer to that is maybe you guys build your own as you already are, and that's how we do it. And this becomes truly an organic Kenyan project, and that's something that we can all absolutely get behind. So more is to come. You'll see Mike and his team will be featured on the Carbon Crowd platform, which other members of OpenAir are developing. This will allow us to sort of create challenges to solve problems in a structured way. That's going to launch in January 1. And so again, those of you who are interested, please do fill out the form. Please follow and really help us make history, I think, with this project. So Mike, thank you so much. And Alex and Charles, thank you so much for joining.
Thank you for having me. Thank you for having me, Chris.